My name is Michael Novick, and for my remote sensing project, I chose to scan the Xfinity testudo statue. There were many different targets I could have chosen, but I went with testudo because of its importance to the campus, its accessibility, and its manageable size. I can easily access all four sides, which will make scanning easier. I did run into some issues with ambient light, which I'll discuss in detail later. Selfies were highly encouraged during the entire process, so I've got a nice collection of images myself as I went along the process. This device uses a LiDAR system designed around computer vision and tracking, and then using geometric relations to determine range. Here's a short clip of the concept early in its development stage. Here's a diagram showing the concept in action. The laser and camera axes are parallel, and the camera field of view diverges very quickly with distance. The laser always stays roughly the same distance apart, so depending on the distance of the object the laser is hitting, it'll occupy a different position in the field of view. Here's a clip showing me demonstrate this concept using the camera and laser separated 12 inches from a distance from 0 to 10 feet. This setup was used for calibrating the instrument by placing marks at exactly 6 inches apart from each other, and then using these measurements to plot a range curve. And offset values were selected such that the measured data matched as close as possible with analytical data. These two plots can be seen overlaid on each other in the bottom right corner of the screen. The match was fairly good, and the two offset values are listed to the right. An important part of this project was developing a field deployable instrument, and this went through numerous iterations throughout the semester. Three main aspects of my design was going to be lightweight, stability, and adjustability. So I ended up using a tripod. I made my chassis out of pine, so very lightweight, and I used bolts and tried to avoid permanently fastening anything in place because I wanted to be able to adjust as much as possible. I have a 15,000 milliamp hour battery that is powering the Raspberry Pi, and I have my separation distance set at 12 inches. Foam was used behind the camera in order to make it more adjustable so that I could make sure the axes were always aligned. This design was a little bit unstable and a little unbalanced, but I ended up moving the battery to the Raspberry Pi side of the chassis, and it ended up balancing out a little bit better. To communicate with the Raspberry Pi, I used VNC with Wi-Fi when I was at home, and used VNC via Ethernet cable when I was out in the field for dependability. I ended up using an analog to digital converter instead of the Arduino for angle collection, which turned out to work really nicely via SPI communication. I don't think the accuracy was particularly better. I also developed a circuit to run the laser via Raspberry Pi GPIO and 3.3 volt regulator. However, I did not end up using this in the field because I could not achieve the same voltage across the laser that I could with the batteries. Here's an image of the circuit. Here's just a short clip of the circuit working. Due to voltage drop across the transistor, I achieved around 2.6 volts to the laser, as opposed to about the 3.1 that it got from the batteries. This was calibrated before I went out to collect data. In order to track the laser, a hue saturation value, HSV, mask is made so that the camera knows what to look for. This is part of the computer vision aspect of the design. So a sample image is taken of the target, and values are optimized so that everything is filtered out but the laser spot. This allows it to create a contour and to find the location of the laser spot only. By performing this on a sample image, we can collect minimum and maximum HSV values, which we can input into our ranging script to collect range values off of our data. The ranging script looks at for just a snipped portion of the screen, the area where the laser can occupy, just a small center right side rectangle, and it collects X and Y pixel coordinates, X and Y positions for the laser spot, as well as the angle. And it outputs these along with the date and time to a text file, which can be imported into other software. Here's an example of the code in action. It snips a small portion of the screen and it tracks the laser dot, as you can see with the red dot on top of the green laser spot. 8 HSV masks were made, one for each face of the base and one for each face of testudo. This is because there is ambient light from the outdoor lights, which cause serious issues for the laser tracking. Vertical line scans were taken of the base and testudo set for a total of 8 scans. These scans are 3 inches apart for the base and 2 inches apart for testudo, because testudo has greater detail than the base. These later get stitched together in MATLAB. Once again, the ambient lights cause significant issues with making a mask that would filter all the other details in the camera's field of view. So many of these problems were resolved in post-processing, removing data points and filtering it out after. Both the base and testudo were aligned separately using MATLAB, transforming the coordinate systems, and then changing offsets in order to make the best alignment. They were then combined together, aligned in MATLAB, and a single text file outputting all of the newly transformed points was outputted and imported into MeshLab. Once the data is imported to MeshLab, first it should not be part of the object needs to be removed. I did this manually using the delete function. Additionally, I set the data to reduce the number of data points and to reduce the complexity that the program would have to process. Then normals to what would be computed, the location of the points around the neighbor. MeshLab is pretty tricky, though it seems to have a lot of powerful tools for people that really know what they're doing. For me, I sort of played with it for a really long time, played with different functions, ball pivoting, and Poisson surfaces, and eventually settled on a mesh that looks pretty close to what I wanted. Here's the final mesh. As you can see, it looks pretty close to the testudo statue. As you can see, the nose was not mapped well and would not come out on the in the mesh. This was due to the interfering problems with the other lights and doors in the background of the initial scans. The rest of the scan came out pretty well. I was happy with that. As you can see in the rear, there's a piece missing. That's due to alignment issues in MATLAB that can be rectified. Overall, the mesh is not quite as straight as it needs to be. This could probably be done with tighter HSV masks and better processing at the end. By the end of this project, I can say I just had so much fun. I learned so much about laser, remote sensing, Raspberry Pi, building hardware, software, incorporating all these systems together, troubleshooting, solving problems. I learned so much, had a great time, and would do it all over again if I could. Thank you.